Hello, class. Welcome back to our discussion of Spot It. So today I want to talk about what properties a 57-card Spot It deck has to have if it exists. And I want to reiterate, we have no reason to suspect it exists, which is why I'm saying if it exists. Now, you might say, well, isn't this one an example? Well, no. As I mentioned in the first video, Spot It decks ship with 55 cards. So maybe it ships with 55 cards and there's just 2 they don't even bother printing, or maybe there's 1 they don't bother printing, or maybe 55 really is the biggest, although I kind of spoiled that one in the first video because I told you 55 is not the biggest. So I want to think about what can I say if I'm now in this specific case that I'm talking about a maximal size Spot It deck, because we proved last time there can't possibly be more than 57 cards. So we're assuming, let's say we actually can. We're just imagining in a fantasy universe that we can get to 57 cards. What can we say about it? And so I want to ask sort of the dual question to the question we asked last time, which was how many cards. I want to ask how many symbols does a 57-card Spot It deck have? Okay, and by how many symbols, to be clear, I mean distinct symbols. So I'm not counting, for example, the fact that the clock is on these 2 cards. That's still just the clock. So if you want, you could ask this as, if I want to actually market my off-brand Spot It deck, how many pieces of clip art do I need to dig out in order to come up with this? So this question actually turns out to be easier than you might at first think. So I'm going to relay out from last time our 8 cards that all have the clock on them. And I claim, well, first I'm going to claim if my Spot It deck has 57 cards, then definitely there is a symbol that it shows up on 8 cards, not any fewer. And here's why. If you look back at our proof that 57 was the maximum number, we started with a card, and then we looked at all the symbols on that card, and the only way we got to this 57 number was, in fact, if actually every symbol on that card we started with showed up on 7 other cards. If, for example, the igloo only showed up on 6 cards, and not 7, then we'd have ended up with a 56-card deck, not a 57-card deck. So this maximum 57 actually only occurs if that first card we chose, when we randomly chose a card, every symbol on that card showed up on 8 total cards. So definitely there has to be a symbol in a 57-card deck that shows up on 8 cards. But next, after I claim that, I claim that now, once I look at these 8 cards, every symbol is here among these 8 cards. There are no additional symbols. Why? Well, it suffices for me to prove that for every card that remains in this deck, all of its symbols are already among these 8 cards. So let me flip this over. So for example, this card, there's a ladybug is already there, so that's already taken care of. The T-Rex is there, so that's already taken care of. The ghost is there, so that's already taken care of. The apple, the OK symbol, the dolphin, the word art, and the anchor. So that shows you, for example, for this card, all 8 of these symbols, they're already there. So no extra symbols for that one. And you could do that. I won't make you watch me do that card by card by card and show that each of these cards already has all of the symbols represented here. But why is that? Well, any one of these cards has to have a symbol in common with each of these cards. That symbol can't be the clock, because we've proven the clock shows up on at most 8 total cards, and that's 8. So that means that each card I pick out has to have a symbol in common with each of these cards that's not the clock. Now, as has come up before, that can't be the same symbol for any two of these cards, because if it was the same symbol, that would be cards that shared both that symbol and the clock, which would violate our axioms, because there's exactly one commonality between any pair of cards. Okay, so, well, that means this thing, all 8 of these symbols, have to end up being used, because there needs to be a symbol that's in common with each of these 8 things, but there's only 8 symbols on this card, so I have to have used all of them, which means all the symbols on this card, and hence every card, have already been used by this point. So that means, if I think about it, there are at most how many symbols? In fact, if I think about it, it's not even an at most. There are how many symbols? Well, the clock plus then 8 for the number of cards times 7 for the number of symbols that aren't the clock on each of these cards, which is 57 symbols used in a 57 card spotted deck. Please note, it's exactly 57, not at least 57, because no 2 of these 8 cards can have a symbol in common other than the clock, because they all already have the clock in common. And so that gives me exactly 57 symbols in total are used. So let me write that out real quick, just for those of you who like to see things in ink. So a 57 card deck must, by previous work, include a symbol that shows up on exactly 8 cards. Call it proof box. Now, every card other than those 8, so all 49 other cards, share a symbol with each of the 8 proof box cards. And not only do they share a symbol with each of the 8 proof box cards, they share a distinct symbol with each of the 8 proof box cards. Because, again, as we've said before, these 49 cards, no one of these 49 cards can share the same symbol with 2 of the 8 proof box cards. But there are only 8 symbols on each of these cards, so that says all 8 symbols have been used already. So thus all symbols on the 49 cards have already appeared on the 8 proof box cards. In other words, the total number of symbols is the same as the total number of symbols on the 8 proof box cards. But what is that total? Well, that number is 1 for the proof box, plus 8 for the number of cards, times 7 for the number of non-proof box symbols per card. That 7 is 8 minus 1, because I took off the proof box that I'm already putting over here. So that number is 57. Good. So that shows us that, in fact, this hypothetical 57-card spotted deck, this mythical beast that we're trying to find, it in fact uses, if it exists, 57 symbols. And if it doesn't exist, then you're probably going to feel like this whole video was a waste of your time. So that tells me, if I write down just a summary now, okay, so we've got 57 cards, 57 symbols. Okay, and every pair of cards share a unique symbol. That's one of our axioms. So let's figure out how many pairs of symbols are there on cards. Okay, so by total pairs of symbols on cards, I just mean something like, for example, this has the pair lock and clown. So I just am thinking about how many ways are there on a card to pick two symbols. Well, that number, there's 57 cards. And, each card has 8 choose 2 pairs of symbols, which is 1,596. So in a 57-card spot-it deck, there are 1,596 pairs of symbols that show up. Now, note, because no pair of symbols shows up on more than one card, these are all different. So I could just say this is just the number of pairs of symbols out of the 57 that show up on cards, because all of these are distinct. Well, then I could ask, okay, how many pairs of symbols are there? Well, that's an even easier question. That's just 57, choose 2, right? There are 57 symbols. How many ways can I pick 2 of them? 57, choose 2. What's 57, choose 2? It is 1,596. The fact that these two numbers are the same tells me something rather remarkable. Namely, it tells me that in this hypothetical 57-card spot-it deck, every pair of symbols actually shows up on exactly one card, because these numbers are the same. And so this is the bijection version of the pigeonhole principle. I have a map between these two finite sets that doesn't repeat, so it's a bijection. And so this is a conclusion. You can call this a theorem. In a 57-card spot-it deck, every pair of symbols shows up on a unique card. Now, you might think that reminds me an awful lot of the second line here, which is that every pair of cards share exactly one symbol. In fact, all that we've done here to switch between the result of this theorem and this key property number 2 is we've switched the role of symbols and cards. Otherwise, they're the same. You don't have to think about that if you don't want to. But basically, these two claims are dual. And so now you can think of this if you want. This is really property 2 prime. But it follows from property 2. So here's where, if you want to make further progress on this question, if you want to actually think about this 57-card spot-it deck and how to actually make one, you have to make a little bit of a leap. Namely, you have to think of all the things in math that I've ever thought about. Do I know of a thing where every pair of a thing determines a unique other thing? And I think you might come up, if you think about this long enough, with the following fact. 2 points in the plane determine a unique line. So this is where the geometry part that I promised is going to come in. I want to start thinking, as I contemplate the idea of this spot-it deck, I want to start thinking about this intuitive connection between symbols are like points I guess this is an analogy, is how I should think about it. This analogy, symbols are like points, and cards are like lines. And how is that? That's because every pair of symbols determines a unique card in the same way that every pair of points determines a unique line. Now, in fact, actually, you might notice this analogy actually goes a bit further, because what happens to every pair of lines? Well, every pair of lines intersect in a unique point. Right? Don't every pair of lines intersect in any unique point? Well, almost. But as written, this statement's not true. What I need is the lines need to not be parallel. This analogy is going to prove very fruitful, except for two large problems with this analogy that are going to have very different ways to fix them. But these two problems are effectively going to be what we're going to fix in our next two videos. But I want to state clearly what the problems are. So problem one is that parallel lines don't intersect. Now, I recall vividly at some point when I was very young, we were on a road trip, and my father said, well, of course parallel lines intersect. They intersect at infinity, which didn't really make sense to me at the time. But we're going to make sense geometrically of the idea that parallel lines intersect at infinity. But it's going to turn out that that's rather difficult to make exactly work. Why is this a problem? This is a problem because if I think about my cards as lines, there is no example of parallel cards, right? Parallel spotted cards would look like two cards that actually have no symbols in common. And my axioms here specifically say every pair of cards actually do have a point in common. So we're going to have to somehow fix geometrically this idea of parallel lines. Problem two, which you might claim is even more glaring, is that lines, at least in the sense we think about them, don't have finitely many points on them. They don't have 8 points on them. Lines have infinitely many points on them. So we need a version of lines that don't have infinitely many points on them. And so, by and large, problem one is a problem with R2. So when we think about the plane, we think about R2. It turns out R2 is not quite the right space for us to be thinking about in order to not have parallel lines that intersect. So we're going to need to introduce this idea of projective space and talk about something called P2 of R. Okay, which is basically an extension of R2 that fixes problem one. And problem two is a problem with R itself. Namely, R itself, and hence R2, is infinite. And so I'm going to need to replace R with a different field. Namely, I'm going to need to replace it with a field that's finite. And this is where we're going to meet the idea of finite fields. And it's going to turn out that we actually want to replace this R with something that I'm going to call F7. Now, one of the many mysteries yet to be discussed, why F7 and not F8? Well, I promise we'll get to that. So the next video, we're going to talk about projective space. And then the video after that, we're going to talk about finite fields. And then we're going to synthesize those two together, and we're going to talk about projective space over finite fields. And then, and only then, will we finally be able to construct our 57-card spot-it deck, which it will turn out is, in fact, P2 of F7. Whatever P2 and F7 are. Again, I promise, after the next video, after the next 2 videos, 3 videos, however, after the next some number of videos, you will know what this combination of symbols means. But, until next time, be well.